was supposed to record this. Alright, good evening class once again. So our topic today is electromagnetic induction. Probably about 4 weeks ago we would have done electromagnetism, which would have been done after magnetism. And we said that magnetism was based on a magnetic field around a magnet, and we'd have learned the magnetic fields. However, electromagnetism is slightly different. Electromagnetism is magnetism produced by an electric current. Now, one of the drawbacks of magnets back then to now is that if you want to create a greater magnetic field, you would have to create a bigger magnet, which means a bigger magnet would means a heavier magnet, and then it would be difficult to use to create motors and generators and so forth. So they came up with the concept of electromagnetism, where you would pass a current through a wire or a conductor, and you would generate a magnetic field. In electromagnetism, magnetism is produced by electric current. So the same magnetic field that you would have had in a magnet is the same magnetic field that you are creating in a conductor. However, to create the ones in a conductor, you will have to pass current through it to generate a magnetic field. When we did the electromagnetic spectrum, we would have talked about the electromagnetic spectrum is made up of two types of magnetic field. Two types of fields, sorry. The first one is magnetic field and the second one is the electric field. The magnetic field originally there, however, the electric field was one generated afterwards. The magnetic field is around the earth, as was explained in class probably about 3 or 4 weeks ago, and the electric field is what we generate when we pass current through any conductor. The magnetic field through any straight conductor is shown here in this picture here. The magnetic field through conductor can be increased during the straighting. So if you want to have a greater electromagnetic factor to increase the strength of the electromagnet, you would have to increase the number of coils. So the more coils, the stronger the electromagnet. The more turns in the coil, the stronger the electromagnet. And the poles have to be closer together in order to become a stronger electromagnet. There's a video I would like us to view. Actually, I'm looking for it right now. Actually, I'm gonna share the screen with you all. So yeah, so would like us to watch this for a moment.
Magnetic field around a straight conductor. Magnetic field around.
Everyone here in the video and seen it. Everyone here in the video? Yeah, good.
Around a straight conductor can be understood by the following activity. Take a flat cardboard and cover it with a white sheet of paper. In the middle of the cardboard, make a hole and through it pass a thick wire and connect the ends of the wire to a dry cell using connecting wires. Plot magnetic lines of force around the conductor with the help of plotting compass. It is observed that the lines of force are in the form of concentric circles. The direction of the lines of force will be clockwise. The experiment is repeated again, but now the current is passed in the opposite direction as shown in the figure. Then the lines of force will be in anti-clockwise direction. If the strength of the current is increased, then the number of lines of force around the conductor increases. This in turn increases the magnetic strength of the conductor.
Good. So as I was explaining in the video, as was explained in the video, sorry, right, as was explained in the video that when a current passes through the conductor, their concentric circles are formed around the straight conductor. These concentric circles are the magnetic field. Now you have to remember that we do not see this magnetic field, neither do we see current. However, we feel the force of attraction or repulsion in them. Unlike poles you would have learned in magnetism, unlike poles attract, unlike poles repel. There were two laws in magnetism. One, the first one would have been unlike poles attract, unlike poles repel, and the second one would have been the force of attraction or repulsion increases, decreases with the distance and separation between two poles. And it's the same thing with the magnetic field here. The magnetic field itself around this conductor will be the same reaction as the magnetic field. How do we increase this electromagnet? The easiest way to increase the strength of the electromagnet, as I explained in the video as well, is to pass more current. So if you want to have a bigger magnetic field, you're gonna pass more current through. Think about a motor, or think about the fan. Your simple fan at home. You want the fan to move faster, so what you do, you increase the speed. You increase the speed by turning the button. But when you turn the button, that means you're going to allow more current to flow into the motor, causing the fan to speed up. That's one. You could also make the fan faster, but the speed faster by increasing the number of turns. In these motors, there are coils of wire, loops of wire that are used to form the magnetic field in the motor. So the more wires you have, the stronger the magnetic field and the faster the electromagnet. The stronger the electromagnet. The poles are moved closer together, so the closer together as was explaining magnetism are the same here for the electromagnet. Any questions on this electromagnet so far? Good. Good. So we're moving on. So some examples of the concept of electromagnetism can be found in devices such as the electric bell as one. The second one would have been the electromagnetic relay. Most of the time we'll find this bell in houses. Bell or buzzer is the same concept. So if you have a buzzer as well, an electric buzzer, it would be the same, right? Another would be the electromagnetic relay, a circuit breaker, a speaker. Um, the speakers that we have is the same concept because they would have a coil in them as well. All right. Later on we'll explain the speakers and how they operate. Good. So these are some basic examples. Another example of the concept of electromagnetism would be motors and generators. Right? Those are all basic concepts that work on electromagnetism as well. Good. Any of one way to know the magnetic field, the direction of the magnetic field, we use the concept of Maxwell's grip rule. I'll show you using the Maxwell's grip rule using a video. Maxwell's. Good. So this is the how the Maxwell grip rule operates. Everybody seen this photo here? This one. Everybody seen this? No. Okay, I'm gonna show this. Um. All right, you all seen this now? This bit here. Good. Excellent. So with your right hand grip rule as Maxwell's right hand grip rule, you can determine the direction of the magnetic field. In which picture you holding your hand in a crunch with your thumb facing upward as in the diagram here. Let's see if I can. Alright? And you pointed the thumb pointing in the direction of the current and your fist your fingers curled pointing in the direction of your magnetic field, your thumb. So in Maxwell grip rule, we say that you point the thumb in the direction, you curl your hand as if you're forming a fist, a complete fist with your thumb sticking out. You point the thumb in the direction of the current flow, and your nails, which are the direction of the magnetic field, or your fingers. All right, so we go back to the lecture here. Everybody still see the Word document? Here, good. So picture this one. If we put with thumb in the direction of this arrow here, the blue arrow that goes down, that means the current flowing down into the wire. What happened is you would see your fingers pointing in the outward direction of the sheet and going back into the sheet. That's why I have the green arrows with the circular in the concentric circle coming out of the sheet in one direction and going into the sheet in the other direction. Everybody seeing? Can you use your hand and do that? Everybody understand how we get the magnetic field and the direction of the magnetic field in a straight conductor using the right hand Maxwell's right hand grip rule? Good. So that's how we know the direction of the magnetic field. There are other rules, for example, there are the right hand screw rule, um, the Maxwell's right hand screw rule, in which is the same concept. Instead of keeping your hand like a fist, you use picture using your hand like you're holding a screwdriver, and you're turning a right hand screw. So using a screwdriver and you're putting it in a screw and you're turning, the direction of the screw rotation is the direction of the magnetic field, and the point of the screw as it goes towards is the direction of the current. If it's coming outwards, then it'll be different. But simple, we could just use this basic one. Um, this basic one here, where you could point the thumb in the direction of the the current flow, and the fingers the direction of the magnetic field. All right. So good. Now so everybody okay with that so far? With the magnetic field for a single conductor? Good. If you're not seeing the screen while I'm talking, just somebody just hit me any messages so I'm gonna buy it. All right. So good. So we're going downwards. So now to deal with a magnetic field between current carrying and carrying conductors. So for C-sec and IGC people, an important thing to note is that you would need to know how the interaction between two current carrying conductors parallel next to each other. Because you would have to draw the magnetic field, especially for IGC and CFC. Recently they have been asking you to draw the magnetic field, whether it be a repulsion or attraction. Good. So this part is particularly important. So the magnetic field between the current carrying conductor, one, the two parallel conductors carrying current in opposite direction will repel. Now, when they're in opposite direction, they repel. Now, think about you, yeah. So for your for think about the current. So when current going into the board, you're piecing your thumb with a X. That means it goes into the board. Everybody see the white screen? I try my best to draw good. This goes into the screen. And this one here now, when you have a circle and a dot coming out, well, a dot is be out of the screen or out of the page. Good. Um, Sorry, my handwriting is so good. Good. Out of the page. Now, how we get these two things? Think about the concept of an arrow. When you shoot an arrow away from you, the only thing is here the back of the arrow is the feather, which is the X part in it. So current will be flowing into the screen or away from you, and if it comes towards you, think about when somebody shoot an arrow towards you, the first thing you're going to see is the point of the arrow. That's why it comes out of the page but into you. So when we for the conductors now, X means it goes into the page, the point means it comes out of the page, the ones with the dot. So let me do the same thing that I taught you earlier. You crunch your fist using the Maxwell's right hand grip rule. You crunch your fingers together and you point the thumb to the direction. So if you point the thumb to the direction that comes out, you will see the magnetic field goes anti-clockwise in this portion here when it comes out. And if you put your thumb and you face it towards where the X is, as it goes into the page, is a clockwise direction. So there's two opposite directional field. On the one where the dot is in the circle here, it is anti-clockwise, and the one with the X is clockwise. So because the two magnetic field are opposite, they tend to repel each other, which is important. You need to know that when the magnetic fields are in opposite direction, they repel. However, we would have learned in the magnetism that opposite poles attract. When current is flowing through parallel conductors, it is slightly different, which is totally opposite. Opposite, when the magnetic fields are in opposite direction, they tend to repel. Good, so you need to pay attention to that. That's the first one. Any question on that so far with the first conductors, first two conductors? I guess no question. All right. For the second one, now we're doing two parallel conductors carrying current in the same direction now will attract, which is important. You need to know how we're going to do that. We're using the same right hand grip rule. Now, the both of them come in way out of the page or into the page. These because it had a dot. Is it coming out of the page or into the page? Anybody can tell me? Anybody knows? I'm just gonna show you again the here, out of the page. Good. So once it have the dot, it is out of the page. You need to make note of that because the lecture do not have that pattern. So pay attention to that. Good. So is out of the page. So as it comes out of the page, if you're using the right hand grip rule again, when it comes out of the page, you realize the direction of the magnetic field is anti-clockwise, which is this on this side here, anti-clockwise, and it's the same for the other side. So on the the right hand side, the direction of the magnetic field is anti-clockwise, and the direction on the right hand side, the left hand side, sorry, is anti-clockwise as well. So both of them is anti-clockwise, which means that the magnetic field would eventually join. So if we see here in the figure here, figure 3, you will notice the inner magnetic field, they make one complete loop. But no magnetic field, the loops are broken. They either go closer together or further apart. That is in this case, because both of them are in the same direction, they tend to attract. So the loop tend to join each other and form. And when they form, it's like a slack rubber band. When you put something around the rubber band and try to pull it away, they try to pull it back together. And it's the same thing. What it does is try to pull the two current carrying conductors together. That is because current is flowing in the same direction. In the same direction, they will attract, and once current flowing in the opposite direction, they're going to repel. You need to pay attention to that, please. So everybody just remember that opposite direction, they repel, and same direction, they attract. Important things to note. Okay? Everybody okay with that so far? Good. I would have right. So nice. So there is some past papers I would have posted for you already um on Google Drive. So what I will do, go into the past papers and do please. Another thing, I'm not sure if Mr. Lyndon would have um informed you, but this Friday we have class of 5 to 8. Everybody know about that, right? 5 to 8 class. Good, nice. So 5 to 8 we have class. Excellent. Um, right. So for the IGCE students, we would be doing this year, this question, which is simple. So there's a worksheet here. Um, so I'd like us to do the first question. So for the IGCE students, whoever have the worksheet, it was already posted onto the WhatsApp group chat for you. So like if you can access it, or if not, you will see it on the screen here. So to pay attention on the screen, the question here says in question 8a, two straight vertical wires X and Y pass through holes in a horizontal card. Figure 8.1 shows the card viewed from above. So you have it's like a cardboard, and you have two X's, not X and Y, but two X's. Two X's means what? If you see the X, what does it mean? The current goes into the page or out of the page? Into the page. Good. Excellent. So it goes into the page. So we're going to place our thumb in the direction of the current going into the page. Because both of them goes in the same current goes in the same direction, what we expect them to do? Attract or repel? If they're going in the same direction, because both of them going into the page. What would happen between the two wires? Because the current, both current for X and Y go into the page, what do you think gonna happen to these two conductors? They're going to attract or they're going to repel? They're going in the same direction, eh? They're going to attract. Excellent. So if you go back here now, instead now, Everybody seen the Word document here that up? Everybody seen the Word document that up, right? Yeah. Well, I should be able to see it now. Good. So here, right, good. Two parallel conductors carrying current in the same direction will attract, and exactly. Shona did say that they were in, both of them was going in, and Angelina said they would attract, which is true. For the figure 3 here that is shown on the Word document, these were both of them, the current were flowing out, but it's still attract. But now the document here shows that both of them are going in and will be the same. So we have to draw, think about we're going to draw now the magnetic field around them. So we're going to use, uh, right, so we're just going to use, all right, so if we think about them, so right, so we're going to have the both of them with the x. So you're going to have x, two x's, which means that they are going into the page. So we're going to see how this going. So you're going to draw two x's like that, or you could use the same document. So think about your finger pointing into the screen. You're going to draw a magnetic field around it first. You need both of them. Good. So if your finger going inward, that means the magnetic field would be like this here. All right, it will be going in that direction. Good. Your X, you're placing your thumb finger pointing into the page, and your thumb would be shown in that direction, right? Wait, I had this one wrong here. Sorry. But let's draw over this. Alright, so into the button. Alright, so let me label this X, Y. Good, so you're gonna have a magnetic field around this one here. Gonna have a magnetic field around this one here. So you're pointing the direction of the arrow to go in, so that means it's going to be like this here. Alright, pick your fingers in the direction. Then the second one, they would be like this. The two magnetic fields will join now. So your directional flow going to be like this. And the third one going to be like this. Alright, you could put as much loops as you wish. However, because I can't draw that good on this board, we have it like this. So your answer should be looking something like this, but much better than this. Alright, in terms of drawing wise. Good, so everybody okay with this answer so far? That's this answer that's going to be here for this one, the 8A. So they ask you to draw, they said there is a current in each magnetic field in a page down direction into the page. So it goes into the page as seen. One, the magnetic field in Y due to the current produces a force on Y. they're asking now, place a tick in each blank column. So, well, we know how the drawing is. A blank column to indicate the direction of the magnetic field and the direction of the force. So the magnetic field at Y, the magnetic field at Y goes where? Towards the top of the page or towards the bottom of the page? Going back and show you the shared screen, the whiteboard, sorry. So where it goes? The one at Y, it was Y, right? Yeah, the magnetic field at Y, the magnetic field at Y, the magnetic field at Y, that's here. Does it go into the page or out of the page? The top of the page, I mean. So it goes to the top of the page, right? So your answer should be at the top of the page for that one and at the bottom of the page. Let me see. To the left and to the right. Um, into the page, out of the page. So those are the answers. So the magnetic field at Y is this one here. The let me share back this. Right. So the magnetic field at Y, they're talking about Y here, would be towards the force. So what's going to happen towards the force? So X is there as is. If it's a force of attraction, that means Y is going to be drawn towards X. So that means it's going to move towards your left. So your answer here should be left for this one. The force on the Y is going to be um, towards the left because you're going to pull it towards it, right? So your answer should be to the left here. Let's see if I could fill and sign this. All right, so that's left. All right, towards the left there, and the magnetic field now move towards the top of the page, towards the bottom of the page, towards the left, towards the right. The magnetic field at Y, it moved to the left and to the right. So you're going in this direction towards the left. You're gonna track it, so yeah. To the top of the page, right? So you're gonna be, if you turn your fingers in a direction, the circular direction, think about you when you place it in the X at Y here, right? You place your thumb going towards Y and you twirl it in a clockwise direction. Your fingers are going to point upwards, which means you're going to go upwards. The magnetic field is going to go upwards. So it'll make a circular direction, but because of the turn, it will be upwards, and your force is going to go towards the Y because it is going to form a force of attraction as seen here. It's going to show back on the whiteboard. Share. So here, what's going to happen is this whole part here going to move towards here. All right. Here, um, we're going to move towards here. There's the force. All right. and your magnetic field is going to go up. Why? Because when you turn the direction, this whole arrow shows like it's going upward here. This arrow here. It looks as if it's going towards downward, but it's really going upward. Because later down you will learn about the Fleming's right hand rule. Um, right, so technically going upward like this. So that's why we get the upward direction for the magnetic field. Good. Magnetic field is usually denoted by B, and current is I. You will learn about that formula later on. Alright. Everybody see the picture that on the screen right now from the whiteboard that I have isn't the best, but so everybody okay with the solution so far for the IGC paper for this question here? Let me share the question. Share. Yeah, good. Right, so they say state and explain whether there is also a force on wire X. Do you think there's a force on wire X? Anyone think that there's a force on wire X? Good, so let's see. So they say state whether there is also a force. So we know that there's a force of attraction, and from our notes here, we would have seen in this document here that the force of attraction operates in both wires. So if we go back to the notes, the question here says, the question here says, state and explain whether there is also a force on wire X. Do you think that there is a force on wire X? Yes, there is a force on wire X because it experiences a force of attraction. Right? Now, because of the force of attraction, it pulls the two wires together, wire X and wire Y together. Good? And because of that force of attraction, they tend to want to pull them together because of the magnetic field. And why the magnetic field tend to join, each individual magnetic field would try to join with each other and create a big loop that will cause the two wires X and Y to pull together. Right, everybody okay with this answer so far? Yes, there is a force on wire X because it experiences a force of attraction. Everyone okay with that so far? The solution, especially the IGC students. Any questions on this portion of the past paper so far? Any questions? On what we did so far? Good. I see Dimitri and Reagan reply. How about the others? There are 8 participants and I get 2 responses. So good. So no questions. Good. And the others? Good. All right. So nice. All right. So we're moving on now to lower in the lecture. The right, so we delimit electromagnetic induction. So there's a parallel, two parallel current conductors. We said, just a recap before we move on, that to increase the strength of a electromagnet, you need to do to increase the strength of an electromagnet. Three things you need to do. You need to increase the current. All right, you need to increase the number of turns, and you need to put the poles closer together. Good. Three important things that you need to do. Um, Also, examples of electromagnets, devices that operate on them would be the electric bell or buzzer, electromagnetic relay, circuit breaker, speaker, motor, generator. Important here for both CXC and IGC, the magnetic field between current carrying conductors. If two parallel conductors carry current in the opposite direction, they will repel, and in the same direction, they will attract, as was just did in our question. Good. So we deal with electromagnetic induction now. What is electromagnetic induction? Electromagnetic induction is the production of an EMF. Another word for EMF here, for most people who don't know, the EMF is also considered as voltage, because we would have done this word when we did Ohm's law. And voltage is basically the driving influence that causes electrons to flow. All right. So EMF, or another word, is voltage. So the production of a voltage in a conductor or a wire due to a change in magnetic field. Important things to know, the magnetic field must be changing. Alright, a change in magnetic field. If the magnetic field is stationary or in one position, for you to generate that voltage, you would need to move the wire so that it would look as if the magnetic field is moving. But the magnetic field is not moving, it's just the wire that is moving. Alright, but it must have a change in magnetic field or a change in direction overall. The effects of the electromagnetic field, the effects of the electromagnetic induction can be investigated in two ways. The first way is using first a straight wire and a U-shaped magnet, where in the diagram here, if you when it is moved upwards and downwards, which is 1 and 2, direction 1 or direction 2, there is a deflection on the meter. You will see the meter moving from left to right, indicating an induced voltage. However, if you move from 3 to 4, there is no deflection. Pay attention to that. Between direction 3 or 4, 3 or 4, there is no deflection on meter. Pay attention to that, because it's not on the notes. If you move between 5 and 6, there would be a small deflection. The biggest deflection that you would get is the biggest deflection you are going to get is between 1 and 2, right? The greatest deflection, the highest voltage. And that is when the conductor is moved perpendicular or at 90 degrees to the magnetic field. All right. So between 1 and 2, you're going to get max voltage. I'm going to put it in summary here. Max it between 1 and 2, you're going to get max voltage. Between 3 and 4, you get no voltage. Why you're going to get no voltage is because it is in the same direction as the magnetic field. I'm gonna put it here. The reason being as I'm perpendicular movement is perpendicular to the magnetic field, For no voltage is because in the direction of the magnetic field, or in the direction of the magnetic field, and between, what's the next number, 5 and 6, you're going to get a small voltage or deflection. The deflection means voltage, right? Because it is at an angle to the direction of the magnetic field. All right, so important thing to note, once it is at an angle, you are going to get a small voltage. For the most amount of voltage, it must be what? Perpendicular. Another name for perpendicular. Uh, movement of conductor at an angle Alright, an important thing to note is that your deflection of meter means voltage. Alright, it gives you the voltage reading. So let's highlight in that. So once the voltage, alright, once the voltage, your one maximum voltage, you would have to move it in 1 and 2. If you want no voltage, you move the wire between 3 and 4. For slight voltage or for a very small voltage, you move it 5 and 6. The size of the deflection would tell you the amount of voltage. The bigger the deflection, the bigger the voltage. Good? So this gives you a summary of how we could notice the effects of the electromagnetic induction. That's in a single conductor. How about now when we use a bar conductor and a coil? A coil means that what? You're going to have more than one conductor, which means that your voltage is going to add up based on the amount of current in each conductor. That means your current should be bigger. So a bar magnet and a coil. When the magnet is pushed and pulled out of the coil, the meter shows the current is induced in the coil in one direction as the magnet is moved in, and in the opposite direction as moved out. So what happens is when I push the direction of the magnet in and out, there's a deflection in the meter. When it goes in, the deflection of the meter is one direction. When I pull it out, it goes back in the opposite direction. Thing to note is that there is no deflection. Think about, but that's when the magnet is moving in the coil. If the magnet is just rest inside the coil here, if you just push the magnet and leave it inside the coil, what will happen is that there's no current going to flow. There's no deflection in the meter, which means that no current is flowing. And as was explained earlier, that the production of an EMF of voltage in a conductor is due to a change in magnetic field. If the magnetic field is not changing, then definitely you're not going to get voltage. How are we going to change the magnetic field? One, if the magnetic field is not changing on its own, you would have to change the direction of the conductor, which means you have to move the conductor and move it between 1 and 2 or 5 and 6 as in this scenario. Or here, you push in the magnet and take it out. The faster you do that, the you put in the magnet and take it out between the coil, the more voltage you're going to get. Good? Any questions on that so far? Any questions so far? Anyone? Good. Nice. So, moving on. Factors that increase the induced. So, how you want to make this voltage bigger now? So, we said that you could either move, when you have the two magnets, you move the conductor in one and two position, which is up and down, or you're pushing the magnet in a coil and you pull it out. How you could get bigger voltages? Important thing to you need to know this because most of the time you ask question about it. So how are you going to increase the induced voltage or the EMF? I'm going to put EMF here in brackets because we consider it as EMF. EMF is called electromotive force, and you would have learned that the electromotive force is the influence that causes the driving influence that causes electrons to flow. How are you going to get a higher voltage? The speed of the motion of the magnet to the coil. So you want to increase the voltage, you move the magnet faster or the coil faster, which is not the coil or the magnet. You're going to move the conductor. So you're going to move this in and out of the coil faster, the magnet, or you use the conductor and you move it up and down fast. Good. The second one with the number of turns. You increase the number of turns in the coil. You can either do it here, as in this coil, or instead of using one single wire, you could wrap it as a loop. You could wrap it as a loop and move it up and down, and you will get a greater voltage. Third one would be the strength of the magnet. The strength of the magnet would be the magnetic field. You could, well, in this scenario, which is case 2, your magnet would have to be bigger. For you to increase the magnet, you would have to increase the size, the strength of the magnetic field, sorry, you would have to increase the size of the magnet. The bigger the magnet, the bigger the magnetic field. Hence the reason we no longer use big magnets. What we use something called electromagnets to design devices from now on, which would be much smaller. However, they could operate at faster speeds and they would have stronger magnetic field. They could operate at higher currents, lower current, depends whatever scenario they are. Good, so everyone okay with this portion of the lecture, the electromagnetic induction? We understand that the electromagnetic induction is the production of an EMF due to a change in magnetic field. And if the magnetic field is stationary, that means you would have to move the conductor relative to the magnetic field. And there are two ways you can show it through a straight wire and a U-shaped magnet, which is the most common for the IGC. You would need to know this. And for IGC as well, you would need to know this one. Here you would have a coil, which is also the same thing, a bar magnet and a coil. So everyone okay up to this point, increasing the induced voltages up to here, I've highlighted in yellow. Everybody good with this so far? Good. Nice. So we move on. So Dimitri confirmed that. So there are just some laws that you would need to pay attention to. We'll go through these now and then take a break. We take a break from around 5:30. If you're okay with that. Would 5:30 be okay? Alright, nice. So it's 5:30. We'll take a break, right? So moving on. Faraday's first law of electromagnetic induction. This is a simplified version. However, there are more difficult version and books that you will need to learn. I would like pretty much if you could learn this and give these people this for exam and get the same mark, alright? So first, Faraday's first law of electromagnetic induction. If a conductor is placed in the region of a changing magnetic flux, an EMF is induced in it. Mind you, this is the first law of electromagnetic induction, which said if a conductor is placed in the region of a changing magnetic flux, now the word changing is important. an EMF will be induced in it. This is exactly what we did. The first law of electromagnetic induction, the very first one we did, which was these two experiments here, where the magnetic field was stationary. However, we changed the direction by what? Moving the conductor wire. The current carrying conductor, we move it between 1 and 2 or 5 and 6 in order to get a voltage. Good. The second law says that Faraday's second law, you would need to know this, all people, CXC and IGC, this is very important. This definitely is important because you need to know this by heart, always. Now, the Faraday's second law of electromagnetic induction states that the size of the induced EMF is directly proportional to the rate of change of magnetic flux, which means you want a bigger voltage. What you need to do, you need to move the magnet faster as opposed to the magnet or the coil faster. So the faster you want it, the bigger the size of the EMF, the faster you're going to have to move it, right? The rate of change of magnetic flux with the speed of the magnetic flux. So you want a bigger EMF, you move the magnet into the coil faster, or you move the conductor in the magnet between 1 and 2 fast, very fast. Right? So that's our Faraday's two law of electromagnetic induction. Good, so everybody okay with that? You will need to learn this by heart as well as Lenz's law. Lenz's law states that, let us go down to Lenz's law. Lenz's law states that the direction of the induced EMF is always such as to oppose the change that produces it. The direction of the induced EMF is always such as to oppose the change that produces it. Which means that, remember, here, in this letter here, where we move this up and down, we're going to get deflection. Based on how your current flow, if your current is flowing from the dark hand to the light hand, and your movement is between 1 and 2, what's going to happen? You're going to get deflection in the opposite direction. That's what we see in here. Alright, more importantly here, the bar magnet and the coil. When the magnet is pushed into and pulled out of the coil, the meter shows the current is induced in the coil in one direction as the magnet is moved in, and in the opposite direction it is moved out. Good. Which means here that when you're pushing the magnet into the coil, the deflection of the meter would go in the opposite direction. So if it goes in, you will see that the current flow goes in the opposite direction, but the deflection of the meter goes in the opposite direction. Good, which is what Lenz's law states here, that the direction of the induced voltage is always such as to oppose the change that produces it. Alright, then we have here now how we're going to determine the direction of the induced EMF. This is Fleming's right-hand rule. So for Fleming's right-hand rule, I like each one of you to stick out your thumb, your middle finger, and your index finger, your forefinger, sorry, your middle finger and your thumb finger at right angles. Alright, so it should look like this here when you stick out your fingers. Um, just sharing something so clear. So you're going to have a direction like this. Let us clear. So you're going to have it like this here. This is your thumb. This is your middle finger. And this is your forefinger. All right, so you're going to stick it out in that direction. All right, this is what you call Fleming's right hand rule. And this rule, importantly, this rule indicates the direction of how things operate. How you will get the current flow. Your thumb shows your motion, your forefinger shows the field, direction of the field, and your middle finger shows the direction of the current. So let us just take this for example here. Pay attention. So F here, this is your motion in your finger. Your thumb finger is your motion or your movement. So it's like when current goes through your field here. This is current, however direction. This is a magnetic field. This finger here, and this is a motion, where I go either up or down. All right, I'll show you when we come back from break, which is we take break from 6:15 to 6:45, a half an hour break. And we will talk about Fleming's left hand rule, right hand rule, sorry. Because there's also a left hand rule. You would see when we go later on. Good. So any questions so far until this point? These three rules you need to know: Faraday's first law, Faraday's second law, and Lenz's law. And they are all one line definitions. I would like you to learn it that way. Please, the one lines. Any questions so far until this point? Fleming's right hand rule, where you separate your fingers like this, all of them at 90 degrees to each other. Your thumb represents your motion, your forefinger represents your magnetic field, and your middle finger represents your current. Any questions so far? So everybody okay with what we do so far? Good, so we're going on break now. So 6:15, we come back 6:45, half an hour break, right? Yeah. All right. I'll see you back in half an hour time. Um, when I get something to eat, I hope I'll do the same thing as well. All right. See you back in a bit. Right, good evening students once again. Continuing from where we stopped off, where we talk about Faraday's law. The first law of electromagnetic induction says if a conductor is placed in a region of a changing magnetic field, an EMF will be induced in it. Second is the size of the induced EMF is directly proportional to the rate of change of magnetic flux. And the third, which is Lenz's law, states that the direction of the induced EMF is always such as to oppose the change that produces it. These are the concepts here of a motor. The first one is a AC generator, and the second one is a DC generator. We said that the Fleming's right-hand rule is applicable to only electric generators. How this operates is that here, for the AC, I would like to pay attention. For the AC generators, there are something called slip rings, and DC generators, there are something called commutators. That's the difference between an AC and a DC. Whereas in a DC, the reason why we have commutator is to draw unidirectional current from the armature winding. Remember, the purpose of a generator is to do what? To produce electricity. The purpose of a motor is to use electricity. Good. So for the generators, how are we going to apply this Fleming's right-hand rule to the generator concept? I would like us to watch a video here, which would help in assisting in understanding. Sorry, AC generator. Right. Everybody's seen this video so far with the AC generator. Everyone seen this video that I have up? Good. Yes, sir.
You will learn about an AC generator. An AC generator is an electric generator that converts mechanical energy to electrical energy in the form of an alternating EMF or alternating current. Working principle of an AC generator. An AC generator works on the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between a coil and a magnetic field, an electric current or EMF is induced in the coil. Parts of an AC generator. An AC generator has an armature ABCD. It is a rectangular coil with many turns wound around a soft iron core. A shaft. It can be rotated rapidly. A field magnet. It may be a strong permanent magnet with concave poles. Two slip rings S1 and S2. These are connected to the armature and thus rotate with it. Two brushes B1 and B2. They provide electrical contact with the slip rings and a load which may be a galvanometer as shown. Working of an AC generator. When the armature rotates between the poles of the field magnet, the magnetic flux linked with the armature changes continuously. As a result, an EMF is induced in the armature. This in turn produces an electric current through the armature and the galvanometer and through the slip rings and the brushes. Note that the galvanometer needle swings between the negative and positive values. This means that an alternating current is flowing through the galvanometer. Direction of induced current. Initially, the armature ABCD is vertical with its arm AB up and CD down. The direction of magnetic field is from left to right. As the armature undergoes a half rotation clockwise, arm AB moves down while arm CD moves up. According to Fleming's right-hand rule, the current will flow in the direction DCBA. So, the current will flow from B1 to B2 through the galvanometer. Now during the next half rotation, arm AB moves up while arm CD moves down. Again by Fleming's right-hand rule, current will flow in the direction ABCD, that is from B2 to B1 through the galvanometer. Thus, the induced current changes its direction every half rotation. Graphical representation of induced EMF. Suppose the armature takes t seconds to complete one rotation clockwise. At time t is equal to 0 second, the armature ABCD is vertical with arm AB up and arm CD down. At this position, when the armature rotates, the rate of change of magnetic flux is momentarily zero. Hence, the induced EMF at this position is zero. During the first quarter rotation, the induced EMF increases. Then, at time t upon 4 seconds, the armature becomes horizontal. At this position, the rate of change of magnetic flux momentarily attains the maximum value. Therefore, the induced EMF at this position is maximum. During the second quarter rotation, the induced EMF decreases. Then, at time t upon 2, the armature again becomes vertical and therefore the induced EMF is zero. During the third quarter rotation, the induced EMF increases but has an opposite polarity as compared to that of the first half rotation. At time 3t upon 4 seconds, the induced EMF attains its maximum negative value. During the fourth quarter rotation, the induced EMF decreases and becomes zero momentarily at time t seconds, as the armature is vertical once again. So the magnitude of the induced EMF is sinusoidal. In this module you have learnt an AC generator is an electric generator that converts mechanical energy into electrical energy in the form of alternating EMF or alternating current. An AC generator is based on the principle of electromagnetic induction. An AC generator consists of an armature, a shaft, a field magnet, slip rings and brushes. The graph between the time and EMF generated by an AC generator is sinusoidal.
Good. So we have seen the AC generator, And what we have learned about the AC generator is that they have slip rings, as was explained here in the lecture. So, seen from the lecture here, for the generator, the simple AC generator here, just as was shown in the waveform, you will notice that each time it turns between the diagonal and the horizontal, there is a upward movement. So you go from when it is parallel to when it is perpendicular is when it's its highest point. Get, and that's the highest voltage you're going to get. And if you could relate back this to the lecture earlier, that's between points 1 and 2. 3 and 4 is where the loop rests, and when it's at 1 and 2, that's where you get maximum voltage. Good, that's at this point in the curve here. We're gonna watch a video now for the DC generator, so we'll see how it operates for the DC generator.
Working principle of DC motor. Working principle of DC motor is very simple. We can see that when the current conductor is placed in magnetic field, it experiences some force in particularly direction. The very basic construction of a DC motor contains a current-carrying armature, which is connected to the supply and through commutator segments and brushes. The armature is placed between north and south pole of a permanent or an electromagnet, an elementary model. One single turn of conductor is placed between two opposite poles. If we start to supply DC via commutator system, current will start to flow. As we see, positive terminal of a battery is connected to left conductor of a turn, and negative terminal is connected to right conductor of a turn. As we see in model, north pole of the magnet is placed near left side, and south pole is placed near right side of the turn. Current in left side flows inward, and current in right side flows outward. As we see, conductor is carrying current and they placed in magnetic field. Both of them experienced mechanical force acted on them. Direction of mechanical force can be easily determined by applying Fleming's left-hand rule. To do this, spread out your left thumb, forefinger, and second finger so they are all at 90 degrees to one another. With that, if the forefinger is aligned along direction of magnetic field, from north pole to the south pole, and second finger is aligned along direction of the current and left side conductor, then thumb indicates direction of mechanical force. Similarly, if the forefinger is aligned along direction of magnetic field, from north pole to the south pole, and second finger is aligned along direction of the current and right side conductor, then thumb indicates direction of mechanical force. Due to this upward and downward forces on the turn, one torque is produced when turn rotates on clockwise direction as shown. After rotation of the turn comes to vertical position in respect of the magnetic field. At this position there is no current in conductor because turn, conductor and brushes rest between two commutators. Hence, there is no force acting on conductor, by due to moment of inertia, turn continue to rotates, and comes horizontal again. Position of conductor has been changed here. That means conductor which was previously in left position comes to right position, and which was previously in right position comes to left position. At that position, we can determine mechanical force, with applying Fleming's left-hand rule. Let's do that. To do this, spread out your left thumb, forefinger, and second finger, so they are all at 90 degrees to one to another. So if forefinger is aligned in direction of magnetic field, that is, from North Pole to South Pole, and second finger is aligned in direction of a current in the left side conductor, then thumb indicates direction of mechanical force. This is clearly upward here. So if forefinger is aligned in direction of magnetic field, that is, from North Pole to South Pole, and second finger is aligned in direction of a current in the right side conductor, then thumb indicates direction of mechanical force. This is clearly downward here. Do this upward and downward forces, turn, tends to rotate in clockwise direction. From that explanation we can come to conclusion that, here in this model we can see that, whichever conductor comes near South Pole, experience upward mechanical force, and near North Pole, downward mechanical force. And do this continuously forces, mechanical turn rotate, even if battery is not connected. Particularly DC motor, rotates, at the same principle like this elementary model. Instead of single turn in DC motor we have mountain turns on major coil. And instead of 2 poles there is number of poles.
Good. So as I've seen here from the videos, now we did a DC, AC motor, we did a AC generator, sorry, in the first video. Second video we did a EC, a DC motor. Now way to pay attention to the DC motor that we did where it had the commutators, which produce the same, operates on the same principle, but with the motor now we use a voltage to produce a mechanical motion. Alright, with this here for the generators, there's one particular formula. We'll not really use that much, however, I'm gonna still show it. So for generators, this formula is used. E is equals to B L V sine theta, where E is equal to the EMF. It's not in the lecture, so I'd like you to take it down. EMF is the EMF. E is equal to the induced EMF, sorry. The induced EMF and your induced EMF and your unit for that is in volts. B is the strength of the magnetic field. Your unit for that is in Tesla, that's capital T. L is the length of your conductor. So you can take down this by the time, because I don't have it in lecture. And the unit design is M. M is meters because it's length. Your V, I have more space here, right? Your V is your speed of motion, the speed of the conductor that's the speed of the conductor, right? And that's given in meter per second. And your theta is the angle the angle between the conductor and magnetic field. I hope this is clear enough. And the magnetic field and unit for that is theta. That's like an angle. Good. Good. So this is the general formula. You are not to learn this formula by heart, neither CSEC. They normally give you this if you need it. So these are what all. This is only for generators. So this portion, everybody get his formula. So for fan, what they mean, what each mean. Good. So everybody get what it means so far, right? So that's you put in that with formula for what again? E is to calculate. You are going to calculate to calculate the induced EMF produced. To calculate the induced EMF produced, and that's what we're gonna calculate that for, right? Now this is only applicable to generators. So you want to find out the amount of voltage that a generator produce based on these four basic things. The size of the magnetic field, which is the strength of the magnetic field, length of the conductor, the velocity, which is the speed at which it rotates, and the theta, which is the angle. As it produce the voltage to calculate the voltage, right, that is produced, or the induced EMF. So you can include that anywhere around here. And what's the purpose? Why we use the commutator is so that current will only flow in one direction. Here, so that it will be in one direction. If you want to reduce a DC generator, would only give a current in one direction, so you only have positive current. In alternating current, you would have a negative current, which means that you have something called frequency. We would have done that when we did circuits. There are two types of electricity: direct and alternating current. Direct current is like battery, where it produce. Once the voltage reaches zero, you need to discard the battery because it cannot recharge. However, in terms of the the alternating current, you would have a frequency because they're both positive and negative. Good, so we're going down now to transformer. We have talked about here lower down, going a little lower down, which is electric motors. We just did the electric motor, and the electric motor, away pay attention with the electric motor. For electric motors, good, we would have dealt with, we just did it in a video. For the electric motor, we would have used Fleming's left hand rule. For the generators, which one we use? For generators, we go back. For generators, we use right hand rule. For electric generators, pay attention, we use Fleming's right hand rule, which is you hold it in the same direction. But now we use this formula here. We use this formula here for the generators. E is equals to BLV sine theta. Good. Now we're going to do generators, and in the generators, now that was generator. Sorry, in the motor, When we dealt with it in a video, they use the left hand rule, which is slightly different. So for right hand is for motors, for left hand is for motors, right hand is for generators. Just pay attention to that. The concept is the same where we use the left hand rule. Your middle finger on your left hand side going to be your current flow. Right hand side, your left hand forefinger going to be a magnetic field, and the direction going to be your thumb. Good, this is the left hand rule. And the same concept with the magnet, whereas you create something called a turning effect from the video. The turning effect of a current carrying coil in a magnetic field. Since the current in both sides of the coil flow in opposite direction, the causes of force, the force produced are also in the opposite direction. So when we watch the video, what I wrote, you realize that it gives it a movement, and one to move up and one to move down, and that's what causes it to rotate as in this direction here. Do you want to increase the speed of the motor? The first thing you need to do is to increase the size of the current. Bigger the current, faster the motor. Stronger the magnet, faster the motor. More coils in the magnet, in the motors, faster. And increase the area of the coil. So you want a faster motor, increase the size of the area of the coil. So instead of making small loops, you make broader loops. Then you need to pay attention to this in particular, how to increase the speed of the motor. Good. Any questions on the motor so far? For the motors, another important thing you need to know this formula for the motors. Um, here, right. So for the motor, we use this formula here. T is equals to B I L sine theta. Uh, Good. So sorry, not T. It should be F. I make a mistake. F is equals to BIL sine theta. Um, right. So that's the force that causes it to rotate. Motors, where F is your force, your induced force, is your force. F is your force. Your unit for force is what again? Newtons. B is equals strength of a magnetic field. And the unit for that is in capital T, which is Tesla's. I symbolizes current, and the unit for that is in amps. L is the length of your conductor, and your length of your conductor is given in meters. And theta now is the angle between conductor and magnetic field. And your unit is theta for that. The same thing just like we had in the last thing. This formula F is equal to BL sine theta is applicable to and I kind of scramble up, so I try my best. Theta is equals to angle the same thing. I'm just gonna write it over here. I ain't enough space here. Good. And magnetic field, and your unit for that is theta, which is means the angle, right? So F is equals to BL sine theta, and this is only applicable for this is only applicable for the motors. Good. Everybody get that so far? This whole thing. Good. So once everybody get that, so we're moving on. So that's applicable to the motors part, so including that here. Anywhere around here, probably after this, where current is equivalent to the I, the stronger magnet is equivalent to B, number of conductors is L, and the cross-sectional area. Well, there's another symbol for that, but we'll talk about that when we're doing that later on. So, two other formulas we would have added, which would have been F is equals to BIL sine theta and E is equals to BLV sine theta. E is equals to BLV sine theta is for generators, and F is equals to BL sine theta is for motors. Good. The force is equivalent to the torque, so just pay attention to that when we're talking about torque. Good. Any questions on the motors? Because we just see a video on motors just now, how it operate, or would you like to see another video? Good. Nice. So we're going on to transformers now, which is the last thing. Now I'd like to pay attention. The, I didn't include that on the notes, but I would talk about it here. So everybody get the formula from the whiteboard, right? This formula. Everyone got this formula? F is equals to BL sine theta.
So
Good.
you could wait. I need to write down one more thing.
Yeah, go ahead now.
Okay, so I finished. Thank you.
All right, good. Nice. So, well, this is for F is equal to. Important thing to note here, when you go to higher studies, they will refer to something called electromechanical devices. Electromechanical devices. There are three types. You can write on this as well, because it's important. Electromechanical devices. There are three types. The first one is generators, which we just do. The second one is motors, which we just do. And the third one is transformer. I would like to pay attention why we consider them as electromechanical devices. Because part of it is mechanical and the other is electrical. For example, in the motor itself, In the motor itself, we had two parts. We had the mechanical part, which would have been the part that builds up the motor, and the electrical part, which would have been the electromagnets that cause the magnetic field for the loops to rotate. Same thing with the motor. Now, the transformer is slightly different. Transformer do not have any rotating parts. However, it is still considered as an electromechanical device because you need mechanical parts in the transformer. And the electrical part is when the current flows through, it produces a magnetic field that cuts and produces another voltage. Good, so take down this here, the electromechanical devices. There are only three electromechanical devices. The first one is a generator, the second one a motor, and the third one is a transformer. The first one is based on what? Fleming's right-hand rule. I'm going to put it as FL Flem. Right. I'm going to put this one here as Fleming's right-hand rule. All right. FRH is Fleming's right-hand rule. Moto is Fleming's left-hand rule. Good. And the transformer have no particular rule. However, they operate on the concept of Fleming's law. No, sorry, not Fleming's, Lenz's law. But both of these operates on Lenz's law as well. Lenz law. However, the transformer is the only one because it have no moving parts. It operates on Lenz's law. Good. Everyone get that so far? Okay. Everyone get that from the whiteboard? Nice. Good. So those are the three types of electromechanical device. Excellent. We're moving on now to the lecture. Continue with the lecture again. On transformer. So we're dealing with the third electromechanical device, which is the transformer. Remember, the transformer do not have any moving parts. However, they are considered as an electromechanical device because it is made of mechanical parts, which is all the steel structure and so forth. And they have the electrical aspect of it, which is the current that passes through it. Good. So a transformer, the major purpose of a transformer is the machine that alters electrical power. Now, this is when we use the term alters electrical power, it does not change the power. The power stays the same. The power stays the same. However, your voltage and your current is what changes. All right. So I'm just gonna say this and make a right. So for transformers, For transformers, power is the same, but the voltage, the voltage, and two, current. These two changes. Right? The only thing that remains the same in a transformer is the power, but the voltage and current changes. We'll explain how that. So remember, a transformer is an electrical machine that alters electrical power. We use the term alter and not because all it does, it changes the current and voltage. Nothing else. The power amount remains the same, but the current and voltage changes. Everybody get the on the whiteboard with the transformer that I just wrote? Good, nice. So what we mean by that? So power, if power is the same, if power is the same, if power is the same, that means you could have the first condition. If voltage goes up, that means current going to what? Current going to decrease. You can have the first condition like that. If your voltage goes up, your current goes down. Or the second condition, if your voltage goes down, if your voltage decreases, your current going to increase. Good. Most of the times, let me just explain. Most of the times here, when TNTech produces voltage, it produces voltage at very high current. The reason why they produce voltage at high current is so that they could transmit it at very low. I'm sorry, at very high voltage. Sorry. When TNTech produces at high voltage, they transmit electricity at very high voltages so that the current would be very small. The smaller the current, less ampere to the wire. Good? The wire going to heat up less. So hence the reason they transmit electricity or electrical energy at high voltages. Now the high voltages typically run on some high tension towers. We call them high tension towers in Trinidad in the electrical grid, and these voltages are typically transmitted at around 33,000 volts, 132,000 volts, 66,000 volts, 12,000 volts, and 6.6 thousand volts. 6.6, I'm sorry, 6600 volts. So those are the different voltage ranges. You do not need to know these by heart. However, what you need to know is that any electrical company transmit electrical energy at high voltages so that its power could be low, its current would be low. The reason being is to save the cables because of heating. We have heating factors that occur in the cable that could damage the cables. Good. So the power stays the same. Remember that your power stays the same. So if your voltage go up, your current going to come down. If your voltage comes down, your current going to go up. That's an important thing you need to know. So when we're doing calculations, which may not be able to roll off today, but from Friday we'll do some more calculations and do some more particles. We could focus on understanding how to do calculations for the transformers. Good. So in the transformers now, continuing, operate based on something called mutual induction. So we talk about electromagnetic induction, and electromagnetic induction was the was the production of an EMF due to a change in magnetic field. Transformers operate on mutual induction, which is when coils are mutually linked together. Good. When coils are mutually linked so that the changing current in one coil causes an induced EMF in another coil. Good. So what we are seeing here is that you have two coils, coil 1 and coil 2 here. When this produces a magnetic field, the magnetic field cuts the other coil because it is adjacent to it and produces a voltage on the output side. Simple operation of a transformer. And I would like if you can learn this exact same thing because this is probably one of the simplest explanation where we say is when an alternating voltage is applied to the primary side of your primary side is typically side that is supply the voltage, right? An alternating current is generated and circulates through the primary winding. So it goes through the winding here and then circulates the core of the transformer. The core now, when it circulates the core, it cuts the primary side, the secondary winding. So when it cuts the secondary winding, it produces an EMF inside here. This EMF is utilized by connecting a load onto it. Good. So let's see if I got a video for you all. Operation of right. So we're gonna
The working principle of transformer.
good. We're gonna watch a video now on transformers so you have an idea about it. And remember we said that a transformer, the power is the same. However, the only two things that alters or changes is your voltage and current. One goes up, one goes down. Good. We also say that a transformer operates by passing a current to the primary side. The primary side is the side that the voltage comes in. The secondary side is where take out the voltage. All right. So we're gonna watch a video how this actually operates the transformer. Pay attention.
Actually, transformer is a machine, but it does not have any moving part. That is why a transformer is referred to as a static machine. A transformer has three main parts: two windings and a metallic core on which the windings are wound. Windings are in the form of coil made of a good conductor of current. The windings of a transformer play a main role in the machine. The winding coils behave as an inductor. When an alternating current is allowed to flow through any of the windings, there will be an alternating flux produced surrounding the winding. The magnitude of this flux is proportional to the magnitude of the current flowing through the winding. The direction of the flux is according to the direction of current. The direction of the current in the winding can be found out by applying right-hand grip rule. This rule states that when we grip our right hand with stretching the thumb along the axis of coil or winding and other forefingers along the direction of current in the coil, then the thumb indicates the direction of produced flux inside the coil along the axis. This flux becomes maximum in magnitude when current reaches its maxima for 1/2 cycle of the alternating current wave. The flux becomes zero when current in the coil crosses zero axis. Again, for next half cycle, the flux becomes maximum but in opposite direction when current reaches to its reverse maxima. In this way, alternating current produces continually varying flux surrounding the winding. The flux lines link the winding itself, and the flux is varying, so there will be self-induced EMF across the winding. This phenomenon is due to Faraday's laws of electromagnetic induction. This induced EMF or voltage, whatever you say, is same in magnitude and opposite in polarity of supply voltage. Supplied alternating voltage causes alternating current in the winding, which produces continually varying flux inside and outside the winding. This continually varying flux produces induced EMF across the winding. So we can say that the supply voltage is caused, and induced voltage in the winding is an effect of this cause. Hence, according to Lenz's law, this induced voltage will be in opposite polarity of supply voltage. Since, according to Lenz's law, effect always opposes cause. This self-induced voltage across the winding does not depend upon the number of turns in the winding, but depends on the supply voltage. But the voltage induced per turn depends on the number of turns in the winding. This is nothing but induced EMF divided by the number of turns in the winding. We have said that there is another winding in the most basic transformer, but till now we have not discussed it. Now we are coming to second winding in the transformer. Supposing one separate winding is brought nearer to the first winding, then this second winding gets kinked with a portion of varying flux of first winding. Due to this varying flux linkage, there will also be an induced EMF across it. This induced EMF would be quite small, as because the flux linkages is small. Hence, rate of change of flux linkage is also small, and according to Faraday's laws, induced EMF across a coil is directly proportional to the rate of change of flux linkage. If now we connect a closed circuit across the second winding, we will get a very tiny current through the circuit, provided the second winding is placed much nearer to the first. So we have seen that some portion of the input power is transformed to output through the second winding. This is because some portion of generated flux of first winding is linked with second. Now, if we want to transform maximum electric power from first winding to second winding, we have to link maximum flux of first winding to second winding. This is done by placing a low reluctant magnetic core in between these windings. Steel is a well-known low reluctant magnetic material, so we normally use steel for making low reluctant magnetic core in the transformer. As soon as we place a steel core in between these windings, nearly the entire flux which was surrounding the first winding will be concentrated inside the core and link with the second winding. As nearly the same flux links with second winding, now the rate of change of flux with respect to time is equal in both windings. Since, as per Faraday's laws of electromagnetic induction, induced EMF across a conductor is directly proportional to the rate of change of flux linkage. The voltage induced per turn in both windings will be the same. We have already explained that voltage induced across the first winding is the same as the supply voltage. Actually, here we consider that there is no voltage drop between supply terminals and the first winding. This is an ideal case. For theoretical purposes, we will consider that condition. As this first winding is connected with supply, it is referred to as primary winding. Now, if this primary winding has N1 number of turns and supply voltage or induced voltage across primary winding is V1, then voltage per turn in the primary winding is V1 by N1. So far, we have understood that exactly this V1 by N1 voltage will appear across each turn of second winding. So if this second winding has N2 number of turns, then total voltage across the second winding is N2 into V1 by N1, and let us say this is V2. If now any closed circuit is connected across the second winding, it will provide voltage V2 across the circuit, and due to the voltage there will be current flowing through the circuit. Normally in a transformer, this second winding is connected with load circuit. This winding is referred to as secondary winding. If the number of turns of secondary winding is not equal to that of primary winding, that is, if N2 is not equal to N1, then secondary voltage of the transformer is different from primary voltage. Now, if N2 is greater than N1, the secondary voltage will be more than primary voltage. On the other hand, if N2 is less than N1, the secondary voltage is less than the primary voltage. The former is called a step-up transformer, and the latter is called a step-down transformer. This is the most basic theory of a transformer. Hope you understand. Thank you.
Alright, good. So, seen from that now, which brings us directly to the lecture again, that there are two types of voltage. So, as was explained, when current goes through here, which is your primary voltage, which is your primary winding, creates a magnetic field that circulates the core. The core is typically made of low reluctance material. Some low reluctance material are steel and iron. That's the two most common low reluctance core um, material that they have. And it circulates the core of the transformer and cuts the secondary winding. This portion is a secondary winding and it produces a secondary voltage. Good. There are two types of transformer. The first type of transformer is a step-up transformer, which means that it has more turns on the secondary than on the primary, than the primary, and the supply voltage, the secondary voltage, which is Vs, is greater than Vp. So that means for the step-up transformer, when you plug in this transformer to outlet, you get a greater voltage. Rather, so if you plug it on 10 volts, you plug in this transformer at a 10 volt supply, you are not going to get 10 volts, you're going to get more than 10, which is 20, 30, 40. Step down transformers now operate reverse. You have fewer turns on the secondary, which means that you get decrease in voltage, which is typically the transformers that we use for small appliances. For example, your cell phone chargers, some of your cell phone chargers or devices, small devices use these where they take the 115 volts and they break it down to a 12 volt or 5 volt. So you go from a high voltage to a low voltage. This is what a step down transformer does. there, are, there are two losses in transformers. The first one is copper loss, the second one is iron loss. Copper loss is based on heat. When you pass any current through a wire, it generates a heat, and this heat is lost through the surroundings. Now remember, we would have spoke about energy conversions, and we said that energy is converted, that the law of conservation of energy states that energy can neither be created nor destroyed, but is converted from one form to another. Why? Because the total universe is made up of one amount of energy, and this amount of energy exists as one amount, but everything around it adds up, which means that it just changes from one form to the other. Same thing here. When current goes through any copper wire, right? Because current passes through the wire, it converts the electrical energy into heat energy, and this heat energy goes to the surrounding. This heat energy is lost as heat. as loss as heat. Now remember, it is not loss, it is just gone to the environment, but it is not productive heat in terms of a transformer. We do not need heat in any transformer because the hotter the transformer, the greater possibility it is for the windings of the transformer to become burnt and damaged. Right? So we try to reduce the heat in the transformer. Hence, we consider it as a loss. And this loss is variable, which means that the more current you pass into the transformer, the higher the heating in the transformer. Iron loss is totally, well, is based on the construction of the transformer. Sorry about that. Based on the construction of the transformer, which means that it is based on the materials that they use to design the transformer. If you use iron or you use steel, those to create the code, those those materials will create a loss in the transformer. We consider them as iron loss, and it is based on the design of the transformer. This loss is constant. The only how you are going to change these losses is by changing the materials you use to create the transformer. Good. So just like you to pay attention to that. The transformer formula is T transformer formula, sorry, is Vp on Vs is equals Np on Ns, which is Is on Ip. I would like you to pay attention to this. This is considered the transformer ratio here, this whole thing. And a transformer ratio, the transformer ratio Right, so this is your transformer. TR means transformer ratio. So this is your transformer ratio here. And your transformer ratio states that the primary voltage over the secondary voltage equals the primary, which is NP, the number of turns in the primary side, divided by number of turns in the secondary side, which is equals to the secondary current over the primary current. Now, we have to pay attention why the current is in opposite. Primary was at the top here, now for the current, the secondary is at the top. Because if we go back to our whiteboard, we said, we're going back to the whiteboard, hoping that I still have it on the whiteboard. Here, the power remains the same, but what happens if your voltage increase, your current going to decrease, so it works opposite, and hence the reason why we use this formula here. TR is equals to Vp over Vs is equals to Np over Ns is equals to Is over Ip, which means that if your primary voltage increase, your primary current will decrease. Then that's how we come about with the increase and decrease to keep the power in one thing. Now, transformers, important thing to note about transformers, here, it's going to write it on the whiteboard. Important thing to know about the transformers. So this was the formula for the transformer here. TR, or the transformer ratio, is equals to the primary voltage over the secondary voltage. It's equal to the number of turns in the primary side over the number of turns in the secondary side, which is equals to the secondary current over the primary current. Good. The secondary current over the primary current means that your current is reversed to the voltage and reversed to the turns. So for a transformer, your power remains the same. However, your current and voltage works as a seesaw. If your voltage goes up, that means your current is going down. The power remains the same. If we go back now to our power formula, there's one power formula which we would have learned, which is applicable to transformers. I'm going back to the whiteboard so that I can write it here. We have learned this formula here. We would have learned this formula. P is equals to V multiplied by I. What is V? V is, sorry, P is equals to V multiplied by I, where we learned that V is your voltage and is given in volts, I is your what? Current. We would have learned that this is something called Watt's law, current, which is given in amps. Good. And P is your power. Now, in transformers, we do not consider it as P. We consider it as S. S is something called your apparent power. This is what, so S is equivalent to apparent power, and it is given in kVA. Good. So that means your voltage is no longer in volts here. Your voltage would be in kilovolts. Kilovolt. Good. So this is the formula that you use in any transformer. If you notice that when you go to any transformer and any of the intake poles, there is a transformer, cylindrical shaped transformer, a gray one, and there's writing on it. There would be something like 50 kVA. 50 kVA is the amount of power it produces, which means that for a particular village, they would be able to supply 50 kVA or 50 kilovolts ampere, right? We would have learned it as watts in DC voltage, but in AC we consider it as volt amps. Good. So everybody get this formula so far? Good, nice. Good, so that's the formula to be used to calculate for transformers. S is equals to V multiplied by I. That's how we're calculating the apparent power of a transformer. Relate back that to this now, to the transformer ratio. Let me go back to the transformer ratio. Here, the transformer ratio. TR is equals to VP on VS is equals to NP on NS is equals to IS over IP. Good. I'm just going to use an example. So we know this formula here. I'm just going to show you how transformers operate. So we're going back to the shared screen again. Right. So let me just say a transformer. Let me say transformer 1. Transformer 1. Good. Transformer 1 shares power of, let me say 10 kVA. All right. Let me just say, sorry, 10. All right. 10 kVA. But we know 10 is equals to, we know S is equals to V multiplied by I transformer 2 now. Let me do with transformer 2. Transformer 2 says S is equals to V multiplied by I. Let me just say now. So this is your first transformer. We're going to call this a primary. So SP, VP, and IP. All this is the primary side of the transformer. The secondary side of the transformer. So we're going to call this S. S, S, S. If your primary and secondary transformer is 10, let me just say all your S's, SP is equals to SS, which is a primary side equals to secondary side, or a transformer. The both transformers given the same voltage, which is around, let me just say 10, right? So you get 10. So if here is 10, you would have firstly 5 multiplied by 2. But now let us just say the same 10 now coming out the secondary side, you will get the same 10. But what are some other things that can make 10? Instead of now your VP being 5, let us just say it now becomes 2. 2 multiplied by 5. Your answer is always going to be the same 10 as you see here. But your VP, what happens to your VP now? Your VP was what? 5 and now we're going to 2. So your VP goes down. But what happens to your VS? Your IS, sorry. So your voltage goes down. I'm just gonna use, sorry, your voltage goes down, and what happens to your current? Your current goes what? It gone from 2 here to what? To 5. So 2 to 5, that means it goes up. Your voltage was 5 first, and then it went to 2. So that means it go down. So as was explained, your power remains the same. So your S is the same 10 here, but you toggle between the two factors 2 and 5 and 5 and 2, but your voltages change. Your transformer is going to be the same size, but your voltage and current changes, which means that your current or your voltage can either increase or decrease. Good. In this scenario, because your voltage decrease, what we call that? Your voltage decrease, but your current increase. We're going to say that is a step down. A step down because why? You go from 5 volts to 2 volts here. In this scenario, I'm just going to show you back. Right? You go from 5 to 2 here. Watch here. So you get a step down transformer. Step up is just the reverse of it. Good. Any question on how the transformers operate? Any questions? Let me see. Good. Nice. So everyone okay with transformers so far? I might just go and wrap up today's class. So that's it for transformers. So we're going back. Electromagnetic, some important things to talk about with electromagnetic induction. Right, so we said that electromagnetism is magnetism produced by electric current passing through a wire. 3 ways you could increase the strength of a magnet. It's through the current, increasing the current, increasing the number of turns, and bringing the two poles together. An example of devices are electric bell, a magnetic relay, a circuit breaker, speaker, motor, generator. For CXA and IGC people, you need to know this. Magnetic field between current carrying conductors. If the current carrying conductors are parallel and the current are in opposite direction, they repel. Same direction, they attract. An electromagnetic induction produces an EMF of voltage in a conductor due to a change in magnetic field. We would have also talked about 3 laws. The 3 laws, we would have talked about first is Faraday's first law of electromagnetic induction, which says that if a conductor is placed in the region of a magnetic change in magnetic field and an EMF is induced in it, which is the first or the second one, the size of the induced EMF is directly proportional to the rate of change of magnetic flux. And the third one, which is Lenz's law, states that the direction of the induced EMF is always such as to oppose the change that produces it. There are 3 electromechanical devices. The first one is a generator, and the generator operates on Fleming's right-hand rule. And in Fleming's right-hand rule, he would have come up with the formula E is equal to BLV sine theta. The second electromechanical device is that of a motor which operates on what? Fleming's left-hand rule. And in Fleming's left-hand rule, we'd have come up with the formula F is equal to BIL sine theta. And then we come to transformers, which is the third electromechanical device. And the only difference between transformer and the generator and the motor is that the generator and motor have moving parts. The transformer is a stationary device. The transformer have one power, however, the voltage and current changes. You have 2 losses, copper loss and iron loss. Copper loss is based on the amount of current that passes through it. Iron loss is based on the material you use to build it. Good. The transformer ratio of for it is TR is equals to VP on VS is equal to NP and NS is equal to IS on IP. Good. Any questions on today's class? Any questions? Good. So I have already posted on to the WhatsApp group chat the the worksheets. You can start the worksheets if you want. Friday will be back here between 5 to 8 to do the solutions for these worksheets and continue wherever we left off. This is the total lecture. However, we still need to do past paper questions to cement what we learned today. Good. So everyone, it's nice for you all tuning in and enjoy the rest of your night. Go through the notes and please attempt the worksheets that were posted on the WhatsApp group chat. I will be back here this Friday between 5 to 8 to work on the solutions for these worksheets. Enjoy the night and be safe as well. All right.